So this should be our last section of notes on section 7-1, finding the area between two curves. We're going to find the area between f of y and g of y. It's always in our best interest to draw a picture of those curves whenever we are finding the area between them, because we need to know which curve's the upper curve and which curve's the lower curve, and where any intersections occur. So I'm going to start by graphing f of y. To graph f of y, we could create a table of values, or it looks fairly simple to factor right here. So I might factor y cubed minus 4y, set that equal to 0 to find my zeros. So if I factor out that y, I'm left with y squared minus 4 equals 0. So it's fairly obvious to see that y should equal 0, or y should equal negative 2, or y should equal 2. So I'm going to have zeros at 0, at 2, and at negative 2. I know it's a cubic, so it should have a lot of curve to it. So maybe to figure out how that curve works, what I could do is I could evaluate the function. I could evaluate f at 1. Let's see. If I evaluate f at 1, I have 1 cubed, which is 1. Minus 4 times 1 is 1, so that's negative 3. This is an x value, remember, so we're going to be left 3, 1, 2, 3, and up 1. If I evaluate f at negative 1, I'm going to have negative 1 cubed, which is negative 1, and negative 4 times negative 1 is positive 4, so that's 3. 1, 2, 3. And we're going to have a cubic function with respect to y, not with respect to x. This will pass a horizontal line test, not a vertical line test, that represents f of y. I also have to graph g of y. Now g of y is a linear equation, but it's written with respect to y. So to graph a linear equation, typically in that form, we just figure out the slope. And we all know slope is changing y over changing x. But when our function is written in terms of y, it's actually changing x over changing y. So the negative 3 as a slope would be negative 3 over 1, which would mean left 3 up 1. So left 3 up 1 will intersect right here. The opposite of left 3 up 1 would be right 3 down 1, so that would intersect here. And I would have this linear equation right here that passes through 3 of the intersections, or 3 of the points that we plotted of f of y, which works out great for us, which is typically what will happen when you have a problem that doesn't involve a calculator. So if you look closely at this graph, or if you were to check it by substituting in negative y, you should see that both of these functions have symmetry with respect to the origin. And so when I calculate my area, the area over here on the left, right here, is going to be exactly the same as the area over here on the right. So I don't have to calculate both integrals. I could just calculate one and then multiply it by 2. So remember, in general, area is equal to the integral from the lower limit to the upper limit. And when it's in terms of y, it's very commonplace to write things from c to d as opposed to a to b. And I like to work with positives, so I'm going to work up here. So I have an intersection from, it looks like 0 to 1, and during that time frame, to the right is higher, to the left is lower, remember, on the x-axis. The upper curve seems to be g of y. So I'm going to have g of y minus f of y. dy. But we had 2 of them, right, to get the total area, because these 2 areas are the same. So I'm going to have 2 times the integral from 0 to 1, that's where the y values where my intersections occur, of g of y, which is negative 3y, minus f of y, which is the quantity y cubed minus 4y, dy. So I'm going to have 2 times the integral from 0 to 1. When I combine like terms, I'll have a negative y cubed plus 4y will give me positive y dy. I'm going going to use power rule here. So I'm going to have 2 times the quantity negative y to the 4th divided by 4 plus y squared divided by 2 evaluated from 0 to 1. So that'll be 2 times negative 1/4 plus 1/2 minus a 0 when we put in the zeros. So I have 2 times negative 1/4 times, or sorry, plus 1/2 is 1/2. And 2 times 1/2 is 1. So the area trapped between these curves here and here combined is going to be equal to 1. Here we're asked to sketch the region bounded by f of x equals x e to the negative x squared, g of x equals 0, and we had that domain restriction that x has to be between 0 and 1. Then we're asked to find the area of the region, and it definitely tells us to use a calculator. So let's graph this. Obviously there's a coordinate plane here for a reason. We know that g of x equals 0 is the line y equals 0, or the x-axis, but I could label it g of x equals 0. X can only go from 0 to 1, so we're going to go from the y-axis to 1. I guess to take advantage of the space, we could put 1 out a little ways. So we're going to have maybe 0, 1/4, 1/2, 3/4, 1. That would make sense. We have no idea as to what our y values are right now, so perhaps we should calculate some of those. So if I wanted to calculate those, I could make a table where I show x and f of x, and because we're between 0 and 1 and going by quarters, we could go with 0, 0.25, 0.5, 0.75, and 1. Told me I could use a calculator, so might as well throw that in. I could put it in as a y equals. So for my y equals, I will have x e to the negative x squared, and I can hit graph. If I trace this at the specific values, I can fill in my table. So if I trace at 0, it looks like I'm at 0. If I trace at 0.25, I'm at 0.235. If I trace at 0.5, I'm at 0.389. If I trace at 0.75, I'm at 0.427. And if I trace at 1, I'm at 0.367. So it doesn't look like I'm getting above a half. Maybe to make it so that I could show the different values here, I could go with the same scale. So I would go with 1, 2, 3, and the 4th line could be 1. At 0.25, I'm at 0.235, which is just less than a quarter. At 0.5, oh, I plotted that wrong. We needed 0, 0. So here's 0, 0. Then at 0.25, we're at 0.235, which is just less than a quarter. At 0.5, we're at 0.389. That's almost 4/10 of the way up, so not quite to a half. .427, that's a little bit over 4/5 of the way up. And then .367, we're back down just a little bit, but not down to a quarter. So I'm going to have a curve that looks about like that. And we're cut off by x equals 1, so we could draw the vertical line right here. That is x equals 1, and I'm going to find the area here. So really we're just finding the area underneath a curve. So to find the area, we'll have the integral from 0 to 1 of, in this case, f of x dx. So we're going to have the integral from 0 to 1 of x e to the negative x squared dx. And I can just calculate that with my calculator. So I can do second calc, integral, lower limit 0, upper limit 1, and finish with .316. That was a nice easy problem to wrap up this section. I hope that section 7.1 goes well for you. Thanks.